Attends, je dois zoomer.
Okay, so hi everyone. Thanks for coming and welcome to this seminar. Today we have the pleasure to have Nina Otter with us today at Sorbonne University, and she's going to give a seminar on the effectiveness of persistent homology. So Nina, thank you very much, and the floor is yours.
Yes, thank you, Julien. So first of all, yes, thank you for the invitation. I'm very happy to be here. I have to be honest, with this view, it's a bit difficult to, I will just try to look on this side. It's a bit difficult to focus. So today I'm going to talk about the effectiveness of persistent homology. And persistent homology, Julien told me that not everybody here is super familiar with topological data analysis or persistent homology, so I'm going to give, let's say, a quick introduction. So topological data analysis, let's say if one had to give it, just describe it in one sentence, one could say that it's a technique in data analysis that uses mostly methods from topology to try to study complex data. And usually complex data is an umbrella term. It's not necessarily precise, let's say, definition, but usually one means data that is high dimensional, might have noise, there might be missing data and so on. It's usually data that is difficult to study with, let's say, more traditional techniques. And so, let's say, methods from topology give, let's say, tools that one can use to try to study such data. There are, let's say, many different approaches in topological data analysis. Persistent homology is the one I'm going to talk about today. But then there are other approaches, for example, persistent magnitude. And then let's say some approaches that might be part of topological data analysis and also other fields like discrete Morse theory. And so I'm going to try to introduce, for those of you who don't know about persistent homology, this is just persistent homology in one slide. So let's take as motivation that we have a set of points, like let me point to it, like this one here on the left. You can think of these as, for example, being satellite images from a satellite of the night sky. And one might be interested in trying to understand, for example, conglomerations of cities, or whether there are some natural barriers. So, for example, here you could think that we have this, let's say, these regions where we don't have any lights. This could for example, sorry, I need to think about Zoom, but somehow I can't. Yes, so it's here. It's very tiny, my cursor. So yes, so basically here one would, for example, this could correspond to a natural obstruction, for example, a lake or something like that. And so let's take this example of a point cloud as a motivation. So for example, here one might be interested in trying to reconstruct how many clusters we have, let's say, of lights in the night sky, and also let's say how many holes we have and where they are placed. And so persistent homology is a method in topological data analysis that allows to do this. So basically one can study clusters, connected components of data sets such as point clouds, and also holes or voids. And the idea is that one can associate, let's say, a one parameter family of spaces to such a point cloud, in which the parameter, for example, in this case is given by distance. So it would be, let's say, thickening the points with increasing, let's say, distance value, and we would obtain this, let's say, filtered filtration of spaces. And we can then, with persistent homology, we can study, let's say, the connected components or holes and their lifetime across this filtration. So, for example, here we would have, and one can then summarize the lifetimes using algebraic invariants called barcodes. So, for example, here we would have the barcode, the blue barcode corresponds to the connected components, so the clusters. And so we are basically, let's say, looking at these lives. So each interval corresponds to a lifespan of a connected component across this distance parameter. And so we would have that at distance 0, we have as many intervals as we have points. And as we increase the distance, so as we thicken more and more, let's say, this point cloud, we would have that some components would merge. And so we would obtain, let's say, less and less intervals. And then at the end, at some point, we have just one component. So for example, here, from here on, we have just this one component. At the end, we have this huge blob. And so similarly, we can keep track of the lifetimes of holes. So here we would have these intervals in pink. And so here we see we have one interval that is significantly longer than the other ones. So this would correspond to this big hole. So for example, again, so in this application of the night sky, one would be able here to recover that yes, there might be some, I don't know, for example, really large lake or something like that. And then there is another interval that is shorter, but still significantly longer than the other ones. And this would correspond to this hole here. And so here, for example, one can just cut through this barcode to the specific distance value. For example, at distance 1.1, we see that we have exactly one let's say blue interval, exactly one pink interval. So we could recover that, let's say, if you were to just look at the components and holes of the space with this thickening parameter, the distance given by 1.1, then we would have, yes, a space that looks like this. And so well, this is useful. So it is useful to use, let's say, this method for data because it gives us very coarse invariants. So, so counting the number of components or holes is something that, yes, in a certain sense, for example, would not be affected by whether we rotate this point cloud, whether we translate it, if you have changes of coordinates and so on. So that's one reason that is a very useful, let's say, yes, invariant or method to study data. And so yes, and more generally, so here we have this parameter is the distance, but we have, let's say, in many kinds of data sets or applications, we have different, let's say, variables for let's say, on which data sets depend. So here it's distance, but it could, for example, be density. If you think about digital images, it could be the, let's say, the intensity of the colors of the pixels and so on. And often actually one is just interested in trying to select one parameter value for which one would see, let's say, would be able to recover some property of importance for the problem. So for example, in this case, we might want to be able to, for example, recover this distance value, but it could also be that we're actually also interested in a smaller holes. And so this is a problem that in general, trying to infer the right parameter value is very difficult. And so persistent homology is very useful in that sense, because we actually don't have to try to estimate the right value for example, here for the distance, but we actually can just consider all possible values of the distance and then study how the properties change, let's say, across these changes of the parameter. And so persistent homology is, let's say, yes, arguably the method in topological data analysis that is used the most. And in fact, people in the field in topological data analysis often complain that actually, that let's say people from outside the field would think that, well, all we do is persistent homology. So actually there are a lot of many more methods, but it is true that persistent homology has been successfully applied to all sorts of different applications. And instead of listing applications here, I thought I would just, so in case you don't know about this, I really recommend this. So this is a database, so it's abbreviated to DONUT. So it's a database of original and non-theoretical uses of topology. And it was first created by Barbara Giunti, and now it's maintained by Barbara, Janice, and Bastian Rick. And Sebastian Rick was able to buy this amazing domain, Donut Topology Works. And so it's basically, it's a repository for papers on applications of uses of topology, so not just persistent homology. And you can with different tags, where is it? Tags, you can search for specific papers. So for example, here with the tag persistent homology, you see there are 282 matches of different, let's say, papers on applications of persistent homology. And one can also, for example, use tag machine learning or look for a specific author and so on. And these are actually only the papers that have been submitted to this database. So yes, if you didn't know about it, I really suggest it because it's really being maintained and updated constantly. And you can even submit papers to be included in the database. But so I'm showing this just to try to give a bit of an idea of, let's say, how widely persistent homology has been used and is being used in applications. For example, here you see these are all recent papers. So persistent homology has been used, yes, to try to, let's say, to study, for example, has been, yes, used to find new subtypes of breast cancer, to predict financial crashes, classify digital fingerprints and so on. So it has really, let's say, applicability in a wide scale of domains. And so I'm going to talk about one specific application on which I have worked. And so the idea for the talk is, so I'm first going to, what the idea is, persistent homology has been applied, is being applied with lots of success in lots of areas, but we don't really understand why. So before going into trying to understand why, I want to first, let's say, touch onto one specific application. And so this is work I'm doing at the moment, I have done, and I'm doing on trying to better understand the climate data. So the motivation here is, well, climate data is definitely data that is, let's say, complex. So there are many different problems with this kind of data. One is what is in the field is called internal variability, which basically means that the signal that one wants to recover is often of the same order of magnitude as noise. So it can be quite tricky to, let's say, to recover signal. And the other is that we have many variables, and so this data is usually very high dimensional. So one would usually actually need to, let's say, project the space onto a lower number of dimensions, but it's often not even clear how many dimensions one would choose. So there are lots of methods that actually depend on the kind of dimension that one chooses to reduce, let's say, the dimension of the space. And so, yes, so there are lots of current problems. Some of these, and I will especially talk a bit more about the first one, the definition of weather regimes, are basically, so the definition of weather regimes is tied to trying to find, let's say, simplifications of atmospheric systems in such a way that one can build, for example, Markov chain models to try to predict, let's say, yes, the weather in the long term. And tied to this is trying to have let's say, long-term weather forecasts, for example, the kind of forecasts that would tell us how the next winter will be like or how the summer will be like, of some of these, yes, main atmospheric patterns that meteorologists observe. And so I'm going to, just to give you a bit an idea of what this would be. So I'm going to give an example of two of the main atmospheric variability phenomena that are studied. One is the North Atlantic Oscillation. So this is basically what one does here. One studies, one studies the pressure over two specific regions over the North Atlantic. So these two regions depicted here. And one usually would have, one always has that the pressure on the region in the north is lower than the one in let's say in the south, and one studies the differences in pressure. So when this difference is very high, then one would have that there are, let's say, winds coming in from the Atlantic. This is called the jet stream, that are very strong and blowing warm air onto Europe, the UK. And the effect that this has is it will, so let's say if we have that the atmosphere is in this configuration, then one can predict that one will have, let's say, warmer winters and also, let's say, wet winters and potentially very stormy ones. On the other hand, if the difference in pressure is, let's say, much smaller than average, then these winds coming in from the Atlantic, which will be much weaker. And so we will have much less of this, let's say, hot air coming in. And then there are also other winds coming in from the east that then will have more chance to bring in cold air onto Europe. And so as a consequence, the winters will be cold, drier, and also snowier. And so, for example, this trying to predict, let's say, in which phase. So there are too many phases. One is what is called the positive phase, in which, so we have this very stark difference in pressure. And the other one is called the negative phase. And so what meteorology institutes like the Met Office in the UK, by the way, yes, this is a screenshot from a video they kindly shared with me. What they try to do is they try to predict in which of these phases the North Atlantic Oscillation will be. And so, for example, this is what allows meteorology institutes in September, October to say, well, next winter we will probably have storms, or next winter will be much colder than usual. And so another pattern that is very much studied, because it also allows to make, let's say, predictions about the weather. So this more globally, because the North Atlantic Oscillation is really more gives indication about the weather in, let's say, Europe and North America in the winter. On the other hand, the El Niño Southern Oscillation gives more global predictions. And so what one does here is one studies temperature, average temperature of the water over a specific patch. Sorry, I'm trying to, yeah, right. This patch here over the Ocean Pacific. And one basically also here looks at anomalies. So we are basically here down, what you see in this graph on the bottom, we are basically tracking whether this average temperature is much lower or much higher than average. And so the red peaks, this is 82, 83, 97, 98. So these were, this correspond to what is called the El Nino phase. And so this means that the average temperature was much higher. And yes, I don't know if you know about, well, these very strong El Nino phases, they brought hurricanes, they brought extremely hot weather. And yes, it's usually not good news if you are in a strong El Nino phase. And so yes, there was also one more recently. On the other hand, if the temperature is much lower than average, then that's called La Nina. And so, for example, at the moment, meteorology institutes are warning that we might be approaching a new, very strong El Nino phase, which of course already with the temperatures being higher than they should be, yes, is worrying on its own. But so also here, let's say there are ways to try to predict, at least to some level of precision, what in which phase, let's say this pattern will be. And so going back to so we'll say something more about the El Nino later, but so going back to the North Atlantic Oscillation, yes, how would one actually do this, have these long-term predictions? Well, the goal is, so here you see actually how the data would look like. Here we have pressure measurements over 2 months. And so you see how these pressure patterns on each day change. And so one would want to try to identify some recurring patterns that at least stay more or less, let's say, in the same configuration for maybe a week or two. And so, yes, so the idea is to find what are called regimes. So this would be, let's say, yes, recurring patterns of the circulation, and one might want to have, I don't know, 2, 5, so that one can then try to set up, let's say, a probabilistic model with transitions between the regimes. And yes, so the problem is there is actually no definition of weather regimes. So these ideas of this existence of weather regimes was first discussed about in the 50s, but there is actually still no agreed upon definition of what a regime should be. And so, for example, here, so this would be, let's say, trying to find regimes in data set, so to try to understand better this North Atlantic Oscillation. This is just one example, let's say, of an approach. One would use some clustering techniques, like, for example, K-means clustering. And in the literature, there are anything from, let's say, 2 to 6 patterns, or let's say, yes, so these pronounced patterns of the atmospheric pressure. And so, for example, here one would see, let's say, in this case, there are 4 patterns, and you see on the left is this positive phase that I was talking about. On the far right is the negative phase, and then there are some other, let's say, pronounced patterns. But then there are many other methods that might also be even more ad hoc than this. So, for example, I was talking about, let's say, these winds, the jet stream that comes in from the North Atlantic. There are some researchers who have studied preferred latitudes at which the wind would blow. And so they would try to then study, yes, clusters like that. But all of this is not very satisfactory because, first of all, depending on the method, one comes to a different answer. And then also each method actually works for a specific data set, and one might not have comparable, let's say, yes, one might not be able then to apply this method to a different data set. So it's all very, let's say, ad hoc. And so another reason this is not satisfactory is that we actually do have models of the atmosphere. So these are, let's say, these are all models of the atmosphere. So the first, for which we do actually have a notion of what the regimes would look like. So any method should also be able to recover, let's say, regimes in these models in which we actually know what the regimes would be. So we have on the left, the Lawrence 63. This is a model that it was in some sense the first model that really convinced people that this notion of weather regime is a sensible notion. And so here basically we would have 2 regimes that would correspond to the wings, to the 2 wings of the butterfly. And here in the middle we have another model, the Charny-Devore, that is more complex. So here we have actually both, let's say, a low velocity and high density blob in the middle, and then this low density loops, but that have very high, let's say, velocity that come out from the blob. And then there is the, yes, Lorentz 96, which is yet another model. But for all these models, there is an agreed upon notion of what the regimes would be. And so, yes, if one tries to look at some definitions that have been proposed in the literature, it turns out that it would fail to try to capture, let's say, the regimes that one would expect in all these models. So here on the bottom right, this would be, let's say, I mean, these are all projections onto, let's say, principal coordinates. And so this would be one way to visualize this, the data set I was talking about. So because in the atmosphere, we would have the pressure and wind are just two sides of the same coin. This is actually, so here we would have, let's say, preferred latitudes of this jet stream. And so we are just, again, it's a projection onto three principal coordinates. One doesn't really see much, it's just a block, right? But so here we would have, let's say that most ways to try to understand whether regimes would fail to capture regimes in at least one of these examples. I think a good maybe system.
So here you just did PCA, right?
Yes. Yes, you see it, PC1, PC2, PC3. So, for example, the Charlie Devore, we have, as I said already before, we have actually this blob in the middle that is very high density, but there we would have actually very slow phase space velocities. And then we have these loops that come out from it that are very low density, but have high velocity. So let's say there is no definition that would be able to capture regimes in all of these systems. So, well, a possible answer, and this is a bit what people have been doing until now, is to say, well, it's basically we see, we know it, right, when we see them. And I don't know if you're familiar with this. This is a court case in the United States in the 60s, where they were debating of whether a specific film was hardcore pornography or not. And so there is this famous phrase or judgment made by Supreme Court is just this Potter Stewart, who basically was saying that he couldn't give a precise definition of what hardcore pornography is. But then if you saw one, he would see it. And in that case, it was not. And so this became very, let's say, it was also, let's say, is a very known phrase, and it's something people use often to just try to try to argue something without being able to give a definition. But of course, I hope you would agree, it's not very satisfying, right? Which is also what was a bit criticized at the time, because it's a very subjective judgment. And in fact, this does end up in arguments, for example, between climate scientists of whether regimes are even real or not. So it is not just, let's say, yes, it really, let's say, creates two debates in the literature. And so, well, if we put our topologist glasses on and we stare long enough at these systems, in some sense, well, we can see these are really just a combination of connected components and loops. Modulo density, which is an important point here. So I'm not going to go much into details about these things, but we can discuss about them afterwards if you're interested. But it is important to keep in mind that one here always needs to threshold by a specific, let's say, density threshold, because, for example, because these are, let's say, these four systems, right? These three systems, the Lorentz, Charlie Devore, and the other Lorentz, these are models of the atmosphere. So, for example, the Lorentz 63, if one were to consider, let's say, too many time steps of a dynamical system, but we wouldn't end up completely filling the two holes into two butterfly wings. And so it's important that we, let's say, consider just points that are in, let's say, very high density regions. And so, well, we can compute these components and loops using persistent homology. And let's say what is useful about this is, what is good about this is we have to make many fewer choices at the pre-processing steps, for example, like how many clusters and so on. And so here, for example, we are able to recover. So here you see, let's say, representatives of the longest lived persistent homology features, so of components and loops. We are actually able to recover what are let's say would be the regimes for these particular systems, what is, let's say, known in the literature. And so Sorry, I have to, and so we think that, let's say, a reasonable definition of weather regime could be that it's really non-trivial topological structure that one can recover with persistent homology. And we are currently working on, let's say, extending this to other data sets, because of course, first we wanted to try to understand data sets for which we would know what, let's say, one would expect to find, to see whether one finds anything reasonable. And so we are currently also, for example, working on studying the El Nino Southern Oscillation. That is a different kind of data set, because that is more, let's say, would be, let's say, a time series in which one is trying to capture some sort of quasi-periodicity about the system. I know there are some people here who work on time series, or so if you're interested in this, I'm not going to talk about this today, but we can also chat about it later. And so, yes, so at least, yes, this might all sound a bit mysterious, but yes.
Sorry, can I ask a question?
Of course, yes.
So you mentioned at some point this notion of periodicity for the regimes. You said that it can be periodic.
So you mean here the El Nino, or?
For instance, yes.
Yes.
And you were showing other dynamical systems where there's obviously some sort of periodic behavior going on in the trajectories. And I was wondering if the cycles that you extract with persistent homology are consistent with the temporal component.
Yes, that's a good question. So in that sense, maybe I can. So we have not investigated that. So that is actually part of what we are planning to do. Sorry, it's one of my very last slides. Okay, it's actually one of the additional slides. Let me go to the end.
I'm sorry.
So no, but I think it's a good question. Actually, so yes. So one of the things we're trying to do is to actually trying to, because there are many of these, let's say, phenomena that are called quasi-periodic, which, let's say, in climate science at least doesn't really have a precise meaning, but it means there's some recurrence. There is not a perfect periodicity, but that's basically what it means. It does not have, in that sense, a precise mathematical meaning. So the idea would be to try, let's say, to use persistent homology to understand better this quasi-periodicity in this phenomena. And so, for example, here one of the main challenges. So one would have a time series. One embeds it. One would get something like a Harper torus. And then one can study the persistent barcodes. What would be important here is to have representatives of, let's say, the important topological features that are actually consistent with the time closeness. Yes. So this is something that we're doing at the moment. Yes. So it's a very interesting question. So I'll go back. Right. So so let's say. Persistent homology has really been used very successfully in lots of applications, but it's often not so clear why it worked. And well, I think at least for the weather regimes, I mean, because it's, well, we are saying about this topological structure, the holes and the components, they can give us information about the weather regimes. But for many applications, it's not so clear. And so let's say one, before talking about that, I want to take a step back, and this is actually the reason that we have this, let's say, title of the paper. It's also motivating the title of the talk. So if you don't know this paper, I definitely suggest to read it. So this is a paper written by Eugen Wigner, a physicist in the 60s. And so he wrote this paper to basically just, let's say, discuss a bit this, what he calls the unreasonable effectiveness of mathematics in the natural sciences. And so basically he was just pondering on how is this possible that mathematical theories that have been developed to explain some specific physical phenomena, for example, the theory of gravity that has been developed to model free-falling bodies, actually then work to explain the movement of planets, right, of planetary bodies. And he makes many more examples like that. And so basically in this paper, he doesn't really come to a solution. And so yes, so I was planning to read a bit about, well, I can read because I think it's really very witty, and I would suggest if you don't know about this. So he says, there is a story about two friends who were classmates in high school talking about their jobs. One of them became a statistician and was working on popular trends. He showed a reprint to his former classmate. The reprint started as usual with the Gaussian distribution, and the statistician explained to his former classmate the meaning of the symbols for the actual population, for the average population, and so on. His classmate was a bit incredulous and was not quite sure whether the statistician was pulling his leg. How can you know that? Was his query. And what is this symbol here? Oh, said the statistician, this is pi. What is that? The ratio of the circumference of the circle to its diameter. Well, now you're pushing your joke too far, said the classmate. Surely the population has nothing to do with the circumference of the circle. And so basically then, yes, he goes on to say that actually, so this classmate, as well as mathematicians, might first think, oh, well, you don't know enough about it, but there is this eerie feeling, as he says, that actually, well, these lots of, let's say, mathematical theories applied to the natural sciences, they seem to work in a mysterious way, and we can't fully explain why they work. And so, as I said, actually, he doesn't really come to conclusion as to why the mathematics is so successful. And in fact, yes, at the end he says, the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. And so that's why he calls it the unreasonable effectiveness of mathematics. And yes, so this is a paper that opened lots of sort of debates in the even philosophy of mathematics. And it's also led to lots of papers with catchy titles like the effectiveness of data and so on and so on. But so, yes, so what does this have to do with persistent homology? Well, as I said, actually, persistent homology is a theory that is very successful, but we don't fully understand why that's the case. And so with my collaborators, Guido Montefar and Renata Turques, we tried to set out some easy data, let's say, shape analysis problems. And we ask ourselves, can we actually, let's say, solve these problems with persistent homology? And so here, I think the fact that these are easy shape analysis problems was for us important because we wanted to really try to understand what actually persistent homology was capturing. And so the problems were the following ones. So, well, from what I said before, well, hopefully we should expect that with persistent homology, we can recover the number of holes. So we studied point clouds in R2, R3, sampled from different shapes. So we'll show this later. And then curvature. So we're trying to understand whether we can recover curvature with persistent homology from point clouds sampled from unit disks from manifolds with constant curvature. And then convexity. So can we detect whether a point cloud is sampled from a convex or concave shape with persistent homology? And before, let's say, even starting our investigation, we had some expectations. So we actually also asked ourselves, well, we wanted to perform, let's say, persistent homology with some, let's say, deep learning or machine learning pipelines. And we had some expectations on what would happen. Well, we said, well, hopefully persistent homology would be able to recover the number of holes and perform even better than deep learning pipelines. Curvature the same because, well, there is this paper, if you don't know about it, by Bubnik and co-authors, which actually showed that we can recover, detect curvature with persistent homology. For the convexity problem, we actually, we thought that both methods will fail. And I mean, now, let's say, a posteriori, I think I would have a different opinion about this. It's easy afterwards. But I think the reason for thinking that persistent homology was not able to solve this problem is just because I had never seen it applied in that way. And I was just thinking convexity is too geometric of the problem to be successfully solved by persistent homology. But it actually turns out that persistent homology can detect convexity. Whether persistent homology outperforms deep learning pipelines, I will say something more in the next slides. By the way, sorry, how I'm doing with time?
We're like 40 minutes in.
Okay.
That's
Did we
fine,
start in time or?
No, like 2 minutes late.
Okay. Yeah. So I have still like 15 or?
I would say how much you need.
Okay, wow. Careful. So I just want to go through this, let's say, 3 problems one by one. I will spend more time on convexity. So, well, for the number of holes, we have some, let's say, theorems, theoretical guarantees that are well known in the field, right? So, for example, there is this, well, very well-known result by Njogis, Nail, and Weinberger, that, let's say if you have point sample uniformly random from a compact smooth manifold, then, so we would have one, let's say, distance value, parameter value, so that we would actually, let's say in this filtration we saw before, there would be one density value, so that this thickened space has the same homology number of holes and components as the original space. Well, this is a good theoretical guarantee to have, right? It's also somehow, it justifies often some kinds of applications of persistent homology, that there is actually one of these parameter values for which we recover what we would like to, yes, the properties of, let's say, the space that we can't access. And so, but so while this is well known, actually nobody had actually, or at least to our knowledge, there had never been, let's say, systematic experimental investigation of, can we actually, let's say, do this, or what are the experimental challenges of doing this with persistent homology, and also might there be other methods that can do this better that we know. And so we looked at, let's say, different kinds of shapes in R2 and R3 with different numbers of holes, so 0 holes, 1, 2, 4, and 9. And then since, yes, it's often also argued that persistent homology is useful because, well, it can deal well with noise, or it's robust in some sense. We also added some, so let's say to each original shape coming from, let's say, from our data set, we would also add some noise or let's say, transformations like translation, rotation, stretching, shearing, and then some Gaussian noise and outliers. And so then the pipeline, so here I'm explaining first, so our, let's say, the main persistent homology pipeline, and then on the bottom there is comparison with some other, let's say, machine learning pipelines. So we would start with our point cloud. We would take a specific filtration, it's called the distance to measure filtration, just because we had added outliers. And then we would, yes, use a specific type of filter space, which is called an alpha simplicial complex, which in this case, since we have point clouds in R2 and R3, it's better suited, for example, than the Vittori-Schrips complex, because one gets sparser, let's say, simplicial complexes. So from a computational point of view, it's preferable. And then we would look, so here we were really just interested in, let's say, one-dimensional holes. So we would look at the barcode just for the holes. And then we would transform this, let's say, into vectors, right? So there are different vectorization techniques for barcodes, because the structure, let's say, of the barcode is, let's say, quite complicated. So if one wants to then use them with some standard classification techniques in machine learning, like support vector machine, one would not be able to use directly the barcodes. So there are some popular vectorization methods like persistent images, abbreviated here with PI or PL. Persistent landscapes. So we used, let's say, three different vectorization techniques: persistent images, persistent landscapes, and then a very naive one, which it would basically just be given by representing each barcode by, sorry, where is the pointer? By a vector of length 10, where we would record the lifespans of the, let's say, 10, let's say, intervals that are the longest. And so this is actually, so this vector of length 10 is what we call pH simple. And then we would, yes, classify this, so use SVM on these vectorizations for the classification. And so we compared our, let's say, this persistent homology pipeline with some machine learning pipelines. So here the most interesting one is PointNet. This is a neural network that has is considered to be state of the art for, let's say, studying point clouds, and takes really the raw point cloud as input and uses some convolutional layers to study specific properties. And it has really been built to be able to, let's say, be, for example, invariant to rotations, translations, and so on. So the other ones here are more, so machine learning, this is simply, so the ML is simply SVM applied directly to the distance matrices. And here, these are just some feed-forward networks. So I think here the most interesting pipeline is, yes, thing to compare persistent homology to is PointNet. And so we have that, let's say, we did a combination of training just on the original data and testing on the original data, or then training on the original data and then testing also on noisy data. Because for us it was, since persistent homology is so useful for applications, we say usually because it's robust to noise, we wanted to understand what is the difference here. So we see here, actually in the, let's say the first, if you train on original, test on original, then we have that both the persistent homology pipeline with the persistent images or persistent landscapes has, let's say, perfect accuracy, but the same is true for PointNet.
Yeah, that's a good question.
Yes.
There's some parameters involved in those vectorizations. So do you try to optimize that?
Yes, also, yes, exactly. So not for the vector of length 10, but exactly for the persistent images and landscapes, those were, yes, hyperparameters that we were tuning. Yes, exactly. Yes. So yes, so that takes some time, but still not the kind of time it takes to, let's say, use PointNet, for example, the kind of, because we also wanted to compare, let's say, the computational resources in terms of memory and time and so on, and it's still more efficient than using PointNet in that sense. Yes. But for us, it was important, right? Because it could be that you have something performs slightly better, but it takes weeks longer, so it might not be feasible. But I think what is very interesting here is as soon as we start testing on, let's say, data. Well, even here, for example, here we are just rotating, right? The regional shapes. We are not even adding noise. And so actually PointNet was, well, designed in such ways to be able to deal with this kind of, let's say, yes, transformations of point clouds. But we see that our persistent homology pipeline still has perfect accuracy, and PointNet is, well, no longer has such good accuracy, right? This would be below 0.9. And then yes, things get much worse when we have, let's say, outliers. Well, in this case, to be fair, with persistent homology too, but it's still performing much better than PointNet. Right? And so yes, and so we also see, for example, here, while big Gaussian noise actually both perform equally well and have perfect accuracy. But so this is what we were hoping, right, to recover. But we were not entirely sure, for example, whether PointNet would not actually also just perform equally well. And it's not the case, at least not in the case in which we are testing on data the network has not seen, right? Which is often a very important problem in deep learning, trying to understand how well a model would generalize to unseen data. So for curvature, so as I said, yes, so there is this, let's say, might be less well known, but still I think well known theoretical, let's say, guarantee in this paper by Bubenik and co-authors, which just showed that one actually can recover the curvature from, so they studied, yes, from a unit disk on a manifold. And the motivation, and so actually this picture I took as a screenshot from a slide by Bubenik, is that, so basically, let's say the main idea behind this theorem, this result, is that if you consider equilateral triangles with circumference radius 1, then we have a precise relationship between, let's say, the depth of, let's say, of the longest interval in the barcode and the different triangles. So for the hyperbolic, we would get this relationship, Euclidean this relationship, and spherical this one. So this is the main, let's say, idea behind this this result. And so for the experiments, but again, we wanted to just make sure that yes, so, and especially also compare, for example, here for us, what was of interest also, well, we were hoping that persistent homology would be able to recover this, but we wanted to compare with, let's say, for example, PointNet. And so we had different shapes. So right, so for negative curvatures, you can really think this disk looks really like, in some sense, a potato chip, right? And then, so in the middle, we have curvature 0. This is in the Euclidean space. And then we have positive curvature here on the bottom. And so here the pipeline would be that we actually, we would actually use the original point cloud just for PointNet. And then for the other, let's say, pipelines, we would use the distance matrix. And then we would for persistent homology, construct the Vietri strips filtration, and then look at the yes, again, vectorizations. So persistent images, persistent landscapes, and then SVM. And so what we found was that what performs best is just looking at, let's say, connected components. So zero-dimensional persistent homology, where is it here? And actually PointNet really fails. So you see, it doesn't really perform that well. And so another thing that we tried out, because so this paper by Bubenik and co-authors, they made the case that actually very short intervals in the barcode are important. That because often those are, one would interpret them as being noise, but they actually said they're important to detect geometric information. And so what we tried is, we basically just took the 10 longest intervals and tried to see whether we could also obtain a good classification, but actually no. Because so if you just look at the 10 longest intervals, you see that we actually have a quite different regression line, right? So we have some failure here. So it really looks like, so we just wanted to test this in the experiments, whether the short intervals are also important. But again, here for us, it wasn't, we were really not sure what to expect with PointNet. Well, you see, I mean, the other pipelines also, yes, can fail dramatically, but with PointNet, we were surprised that it would not perform that well. And finally, so we'll try to not take too much time, but so, so for convexity, there were no theoretical guarantees. And so we thought about this for a long time. We wanted to, so our idea was to try to find some kind of filtrations that for a concave shape like this would, for some parameter value, be able to detect more than one component. And so basically at the end, what for us turned out to work well is what we call tubular filtration. So the idea here is that we consider a line. So this would be this line alpha. And then we consider all the points at a specific distance from this line. So for example, here, this would be, in green would be all the points at a specific distance from this line. And for example, here you see that if we were to choose that distance, we would see two components, right? Because we are only considering the parts in green. And so this is basically the, so the main idea. And there are lots of, let's say, high filtrations that have already been considered in the literature. For example, you might also be familiar with the persistent homology transform that is based on considering height filtrations with respect to specific directions. And so the way our, let's say, this tubular filtration compares is that it really makes a difference, let's say, in dimensions higher than 2. So because in, let's say in dimension 2, if you look at this shape, then you would have, let's say, the tubular filtration with respect to this line would actually be the same as considering the height, let's say, distance from a hyperplane. And but on the other hand, in R3, and this is really what allows us to detect concavity just with zero-dimensional persistence, is if you consider this, let's say, to be a empty, so to be a sphere, right? So we would actually have a void inside. Then with both of these filtrations, we are not actually able to, let's say, the part in green is just one connected component. Also here, right, we have a hole, but it's one connected component. Instead here, we are really cutting out two disks, right, on the two sides. So this is what allows us to, because here we consider all the points at a specific distance from this line. And so yes, so basically the main idea is that, so with this kind of filtration, we can look at just the number of components. If you have one connected component, then our shape is convex. If you have more than one, it's concave. And so this would basically be the result would be that we look at the tubular filtration with respect to any line, and then the shape is convex exactly when the zero-dimensional persistent homology of the filter space contains exactly one interval. And so the main idea behind the proof is that one is basically for a concave shape, one would try to identify a line for which one sees more than one component. For example, here. So in this case of this shape here, for this line, we would see the two components. And then, yes, and then we did, so we wanted also to test this experimentally. How well does, for example, persistent homology now compare with respect to these other pipelines? So we consider different kinds of shapes. First, let's say what we call regular convex shapes like triangles, squares, and so on. And so here the label would be this is convex and this is concave. And so here also some, let's say, basically just equivalent concave shapes. But then we didn't know if you just had such regular shapes, what would actually these algorithms detect? Would they actually just learn the shapes or something else? And so basically we also added some what we call, let's say, random shapes. Here we really just chose points randomly and then constructed the convex hull. And so we have basically also, and these are really all different, let's say these random shapes. So we have both convex and concave ones. And so what we then did is, so we would transform each point cloud into an image so that we would be able to use cubical complexes. And we then looked at 9 different filtration, let's say, directions, right? So these tubular filtrations. So these are the lines that would be given here, the directions. So for example, in this case, so here, the one on the top, so we're considering the distance from this line that passes through here like this. So you see at first we don't have much, and then we have slightly more until we have, let's say, the whole shape. And here, this example here would be with respect to the line passes through here. And so we are basically just filling it up like this. And so the idea is that if you have a shape that is concave, then there would be one of these directions from which we would be able to detect this concavity. There would be one direction, for example, here. This is one direction from here. We actually see here we have 2 components. And yes, in practice, it might be the case, and I will show you some examples for which these 9 directions are not sufficient. But let's say, for example, here we didn't have those many examples for which it would fail, and one can always take more, let's say, high resolution images or more directions and so on. But so what we did is we considered these 9 different lines for which we took the filtration, and then we considered just, so persistent homology dimension 0, just the components. And then we would look at the maximum lifespan of the second most long-lived component, because, well, we always will have one long-lived component. That's not interesting. What is interesting is the second most lived one. Because, for example, like here we have 2 components. At some point, this will just merge in one. So actually, if you have a very long-lived second, so if the second most persisting component is very long-lived, this will mean that we will have, let's say, a source of concavity. And then we would, yes, use SVM on this. And so the results are, so if you train and test both on these regular shapes, so the triangles, the squares, and so on, then both this persistent homology and PointNet, they have perfect accuracy, right? But again, as I said, if you just look at these very regular shapes, it's not clear exactly what we're learning. And so, yes, so in fact, it turns out that and so yes, we try different combinations. We train just on the random concave convex shapes. So we would have, so we still have, yes, let's say everything performs worse, but we still have persistent homology performs better than PointNet. If we train on regular tests on random, we have, yes, again, let's say better performance by persistent homology. And then, yes, finally, we train on random, test on regular. So here it seems, right, so here this is also to be interesting that we train just on the random shapes. Persistent homology is able to have a very high accuracy, right, on the regular shapes. So it is, since it's learning something, let's say, well, intrinsic about convexity and concavity, whereas PointNet, it's not clear, right, what it's learning. It's actually performing as badly as the very naive deep learning pipelines. And so, yes, I just wanted to give an example of, let's say, wrong predictions. So with persistent homology, these are point clouds that were, let's say, that are concave. Yes, concave, and were actually, let's say, predicted as being convex. So as I said, this can happen. It just means that we basically, of these 9, because there were fixed directions, 9 directions that we chose, none was able to detect these sources of concavity. So there are different things one can do. One could, for example, in applications, add more directions. And we were also discussing some sort of semi-randomized way to choose the direction. So
there's a question of scale as well of the feature. Sometimes you can have very small convexity.
Oh yes, yes. Of course, it depends exactly. Yes, on yeah, exactly. I mean, exactly. If you have very small convexity, then there you also have a problem. Yes. And of course, this also then depends what one does. Also, specifically depends on the kind of application, right, that one has. And so, yes, so in fact, so I wanted to show, let's say, an application that we worked on. So we wanted to try to see, well, so we went through this, let's say, fundamental shape analysis task, but our motivation was to try to understand actually why persistent homology works in actual applications. So this data set of plant leaves. So this actually, so here on the left, the column on the left, you have the raw images, and so what we did here is we considered a measure of convexity that is given by considering the area let's say, of the image. So this would be, for example, here the area, this pixelated, the black area, divided by the area of the convex hull. So the convex hull you have depicted here. And this is a measure of convexity that has been shown to be very useful in classifying, let's say, morphological classification of, for example, yes, of plants and so on. And so actually here you have the leaves, the way they ordered the rows, we have, let's say, decreasing convexity measure. And so we would have, yes, this has higher convexity measure than this and so on. So yes, so it might seem surprising, right, that this has higher convexity measure than this, but it is because we are actually, let's say, taking the area, so it's proportional to the area actually of, let's say, the image. And yes, and then we're taking filtrations according to 9 different directions. So here it's just, I mean, just 4 directions because it wasn't fitting on the slide. So, well, for example, here, this is an example in which you have lots of sources of concavity, right? And so, for example, here we are taking the filtration starting from this direction. And here is the filtration. So we have a line, the line would be here. So we're going down. Oops, sorry. Here we are taking the line like this. Sorry, I don't know. But so yes, so we are basically taking the line on this corner. And here the line is instead, is actually cutting through the leaf vertically, right? So we are basically starting from a line in the middle and then increasingly taking on the points to the left and right of it. And then we have here the barcodes, the persistence diagrams that capture, let's say, how many, let's say, very long-lived components we have. And so as you see, and right, we're interested in actually looking at the lifespan of the second most lived one. And as you see for some of these, because here we have lots of sources of concavities, we have, let's say, more than just 2 that are above the diagonal, like here, for example. So we might have multiple long-lived components. And then, so what we did here, because this was now a regression problem, right? Because we have this continuous convexity measure. It's not just about classifying is something concave or convex. We wanted to know how convex is something. So what we did, we actually did not just take the lifespan of the second most lived component, but we actually took the lifespans of the across all the different. So basically, for each for each filtration direction, we would look at the lifespan of the second most lived components. We would keep those 9, so we have 9 different lines, directions, and then we would sum those up. And so actually, so here we have the, let's say, the concavity measure across images. This is just taken by having 1 minus this convexity measure I showed first. So here you would have this sum of lifespan. So you see there is actually a very good, let's say, yes, I would say, yes, correlation between the two. And so here we have that we actually can achieve fairly good prediction of this convexity measure with persistent homology. And then, of course, this can be refined. So, for example, I think it was for this particular leaf, because it has also sources of concavity, that actually we did not achieve a very good, let's say, prediction. But again, so this one can refine this. For example, here we just kept track of the second most lived, I'm done now, right?
Oh,
okay. Second most lived component, but one could also decide to keep track of the third and fourth and so on, right? Because here we have, because right, as you see here, we might have very interesting, let's say, yes, sources of concavity that one is able to capture in that way. And so for us, this, let's say, this application was important because we actually, so here with persistent homology, we are, so here we are able to classify these leaves because we are able to actually detect concavity convexity with persistent homology, right? And we're using this measure of convexity. So for us, this was an example of, actually here it's successful, and we also do know why, because it's actually detecting convexity and concavity. And so what we're doing in current future work is the idea would be to really try to understand, let's say, take some very, let's say, well-known or successful applications of persistent homology, try to investigate why it actually worked in those cases. And so along this, for example, one idea would be to try to investigate the relevance of point cloud points for specific topological features. And of course, these are, I mean, these kind of interpretability questions are very, let's say, well studied, or hotly, yes, these are very hot topics, for example, in neural networks or deep learning. So there are lots of techniques that we might want to, let's say, try to combine our approaches with existing approaches. And yes, and with this, over. Thank you. So, and here are the two, let's say, the two papers I was talking about, yes, the two main references.
Do you guys have questions for Nina?
Yeah, I have a question about the transportability of coordinates. And in the first slide that you showed that compare distance homology to coordinates, like we see that with the translation there is a huge drop in performance for coordinates.
Mm-hmm.
And I was wondering if there was an easy explanation of that, and if we can say what does that? What happened?
I
don't know
don't.
if you have any information about that. Or...
No, I don't have. No, I don't have the explanation. But I mean, of course, I mean, I have to right. So of course, let's say in this comparison, we did not try to optimize the other pipelines. I have to be. So this is important to say, because ultimately for us, it was really not about trying to say who is the winner. It was really more about trying to understand does persistent homology work, and also try to compare with other techniques out there, but it was not, we would not present this as state-of-the-art comparison with the most advanced deep learning architecture, because then we would have been building that too. Because, for example, to achieve invariance to translation, right, that are methods that are used. So, for example, using, let's say, max pooling, right, or things like that, we could maybe have tried to add some layers or some things like that. So we did not. Yes.
You guys have other questions? Just any question is good. Yeah, I asked no questions. Well,
maybe it's a stupid question, but on the slide when you try to use persistent homology to find the regime of the non-arithmetic jet, like trying to making it correspond to the three classical regimes. I think you try to compare like maybe first dimensional homology groups to the 0, 1, and I was wondering why you were doing that if the dimensionality are not the same.
Yeah, sorry, I'm just I don't know why it's not. Wait, just trying to go back to that slide. Here. Yes, no, sorry, there was this one.
Yeah.
Because like you're watching the cycles and the three classical regimes, but on the North Atlantic jet, it seems like you're watching the
components, just components, yes. So here we don't have, so on one hand, the North Atlantic oscillation is not thought to be, to have any kind of quasi-periodicity, like for example, other weather phenomena like the El Nino. But so again, so this is a very interesting question. How is periodicity related to the fact that one would find loops? So here, yes, with let's say the interesting. So it's actually also in let's say in standard techniques to try to study this. It's actually usually people really try to find clusters. So there is no, let's say, at least also we did not find any interesting loops, and actually the clusters we found, they were consistent with let's say regimes that are known to exist, let's say, in the literature. I don't know if this answers your question, or
you found two clusters, and so you.
It's actually so yeah. So I'm it's actually you see 2.5 or something.
It's corresponding to the Lawrence 63 region.
No, sorry, there is no correspondence.
Oh, okay.
No. The colors are actually the colors are so no. These are all, let's say, different systems studied with persistent homology, but there is no correspondence, or at least not in that sense. So the color codes are basically just the I think we always used pink for the longest lived, blue for the second longest lived, and so on. I don't know if it.
I think maybe Ken's question was: is that the low pressure in pink and the high pressure in blue, right?
Yeah.
Because you showed us at the very beginning of the map that there was two.
Yes, I do actually don't have it on the slides. I have it, I just need,
Okay.
yes, if you just give me a second, I can show it actually what this corresponds to. It's not exactly the positive and negative phase. It's almost like that. Yes.
Okay, okay.
Yes. But yes, I can show it to you, but maybe I would just first need to browse through my laptop to put it up and show it to you. Yes.
Do you guys have other questions? Yeah.
Yeah, and so on this one, I was just wondering, since I'm not sure what's the pipeline in this case, so you get a time series and then you take to build your simulation complex, then you take the time series in delay embedding.
So you're asking for this or for the other ones?
I just wonder in general how do you approach
Yes,
because
so-
I guess you got your data set. It's like a time series.
Right, so for the North Atlantic jet, actually one has more, sorry. Well, I mean, one would have more, let's say, it could be, for example, pressure measurements over usually as 100 years over the North Atlantic. And then one would, well, this is then, let's say, would be very high dimensional space, and one would have different ways to, let's say, to look at principal components. So it would, but here in this case, we don't really, we would not consider time as being, let's say, a separate variable. We don't consider this as time series. There are lots of different approaches. But so, for example, yes, and so, for example, yes, the other ones would be more time series, and yes, then one looks at the time delay embedding, like this example I gave earlier on the other slide. So one would embed this.
And then the filtration you use always like implies a metric, like as in it's always some sort of trips.
So in that case, yes, we use trips. So yes, so for example, yes, for the other ones, we were doing more something like this. So we would have a time series and then embed it into Euclidean space. In any case, we have point clouds, yes, in Euclidean space. So in our case, yes, we use trips. Yes. I know, I mean, there is lots of details, right? I swiped under the rug, but because Julien had asked me to talk about both papers, so I tried to combine them into a coherent talk. As a result, I can't, yes, I didn't say everything, but yeah.
The mix was great though. If you guys have questions online, don't hesitate to write them down in the chat window, and I'll be happy to ask them for you. In the meantime, if you guys have other questions.
So did you try to convert the point cloud into a measure with and then putting it in CNN? Because
sorry, this is about the weather or no?
Converting the point cloud into measure resistant to measure with for instance a connection with the ocean or something like that, and looking whether it can see the oil in with the CNN, because
with the CNN.
Because
so, but you're talking about the weather.
The first application.
Yes.
The application about the oil.
In the second part of the talk, when you're doing the whole detection.
Because the dimension one homology
here,
not even before the curvature.
Here, the holes.
The number of holes. Because in fact, it says that the first layers of CNN look at some at the holes and something like that.
But no, we didn't look. Well, I mean, PointNet does have convolutional layers, right? So PointNet does have convolutional layers in the model. Yes, there are convolution. I'm saying no, we did not do.
Pointwise or at the scale, the whole scale? I think it's pointwise.
What do you mean by pointwise?
They make comparisons point by point. They don't. Pointwise, maybe.
If it gets too technical, maybe.
But so yes, no, we didn't. But again, yes. So because ultimately, one, of course, I mean, it's also a bit, for example, the point made by Wegener, right, in his paper, that how do we know that there is not an alternative out there? We haven't explored that. We would come up by disregarding the things we care about the things we don't care about here, and that would explain all this in the same way, right? So it's not, we don't claim we have explored all the possibilities in deep learning, right? It was more to try to to see can we actually solve this with persistent homology, and we can write in a very satisfactory way. We can actually solve it.
If I may, I have a couple of questions, and then I promise after
Yes.
we can have a break. I really like the applications with the leaf classification. I think it was really relevant, and I was wondering if he had a sort of a similar application for the hole detection.
Oh, for the hole detection.
For instance,
You mean in mind to try
if
to
you have some
explore?
data sets, some real life data sets annotated by experts with actual periodic patterns or loops.
Well, I think, I mean, because we have been discussing among us, right? Because for us, well, we would really like to try to, let's say, do this kind of investigation for, say, success stories of persistent homology. There is this paper by Catherine Hess and co-authors on classifying nanoporous structures. And there, it really, to me, it seems that might be the kind of application for you to really have. You have a very rigid structure with different kinds of concavities, holes, and so on. And so, for example, that could be, but we haven't done it yet. So, but for example, to me, that seems the place to look because it's very regular, right? Okay. Because they have actually these models of these different materials. Yes.
That's a good example. And last, I will ask you the same question I always ask in the topology talk.
Hola.
And I'm just trying to collect the answers and I make polls.
So it's part of your statistics.
So you showed us very interesting examples of persistent homology in dimension 0, 1, and 2.
Yes.
And I wonder if you could say something about the higher dimensions.
Yes. So that's actually that's why I think persistent homology, that's why I think, for example, trying to study the Ninius-Houghton oscillation or this quasi-periodic phenomena is per se a very interesting problem for TDA, because I don't know of that many applications in which we actually can give meaning to voids or higher dimensional voids.
Actually, I saw this 3 cycles.
Exactly. And so actually here the thing is that, well, if you have this quasi-periodic time series, so which actually it does have a precise mathematical sense, right? We would have, let's say, we would have a function that depends on time, and we have different frequencies that don't have, so that their periods don't actually have a rational relationship. Right? And so usually this approach to model well what are called quasi-periodic phenomena in the atmosphere. So if we embed this, and here one has to be careful as to choose good embedding parameters, but what we get is a torus in, let's say, high dimensional space, and let's say how high that dimensional space is depends well on the embedding parameters and so on. But so let's say here what I think will be important is that well, not just let's say the cycles, but actually let's say how, because so if you look back at this here, actually the color codes are giving us, so if you follow, let's say, the blue, and then we go to cyan and so on, so we're actually following in time. Yeah. And so you see this, since here we see some regularity, right? Because we have the peaks, let's say cyan, and then, so we do see we have some kind of repeating pattern, but it's not perfect, right? So we would have these 3 peaks and so on. And so since this is not perfect, this is not, if this was perfectly periodic, you would just get something like a circle, right? But so this is something that is wrapping around itself and so on. And so here I think that really, well, the lifetime of the voids, of the cycles and so on will be very important to try to characterize better this quasi-periodic, this recurrence of these events and so on. So I think that's why I think this, I already find it interesting per se, but it's very interesting application for TDA, because it's one of the few ones that I know where we can actually, I think, really give meaning to these higher dimensional features, and for which they're actually also important.
But you're talking about higher dimensional, you're talking of the 1 cycles, or?
No, I'm talking about, let's say, 2, 3, and so on. This was your question, right?
Yeah, absolutely. But then I thought you were, the periodicity of the small patterns, I thought you were relating it to the.
Oh, well, because the thing here is this is actually higher dimensional, it's just also projected, right? Okay. But here we actually do have not just voids, but also 3 sides. So voids, absolutely. Right? So you just don't, well, you don't see them here, but they are there. So that's why it's, I think, everything together. And in what way exactly, I can't tell you yet, because I'm working on it now. But I think this will be very important to try to understand these recurring patterns in the atmosphere and so on. Yeah. So I hope I will have a good placement in your statistics or whatever you have. I hope I'm in the top 10
I
or
wish it was on
something.
the slides. So. No, that was very, very interesting. All right, so I guess if there's no more questions, we can thank Nina again for this excellent.